You should have out lecture 16 notes, empirical probability and the law of large numbers. Again, our context is, from the previous lectures, we have a random experiment that results in a sample space S of possible outcomes, and we're looking at some event E, which is a subset of the sample space, right? And I say here that instead of computing the probability of E by measuring the relative size of E as a subset of S, which is what we were talking about last time, that's the classical or theoretical way of getting what we would think of as the true probability of the event E. What we can do is we can estimate the classical probability by finding the empirical probability. We just perform the experiment many, many times and keep track of the relative number of times the event E happens. That is, what you're sort of doing is we're generating a sample of data, a sample of the outcomes of the experiment from the population of all possible all possible times we perform the experiment, all the outcomes we could generate if we just performed it forever. We'll just do that for a certain length of time, a certain number of times, and we'll have a sample of outcomes of the experiment. And what we will do is we'll compute the relative frequency of E in that sample. So this is going to look like stuff we've done before. So what I'm saying is that for the empirical probability of E, we write the probability of E is, now this is empirical, which we've already talked about, or I've hinted at a little bit. And what I said is it's the relative frequency now of E occurring in the sample we collect. So in other words, if we think of it as performing the experiment over and over and collecting the data from the resulting sample of data, we think of it as the number of times E occurs divided by the number of times the experiment is performed. All right, this is different than the number of outcomes in E divided by the number of outcomes in the sample space, right? That's utterly theoretical. If you notice in all the examples we did prior to now, we didn't talk about ever actually performing the experiment. We just sat down and thought through what the outcomes would be, and we looked at the cases where they were equally likely, and we just computed the relative size of E in S. Now we're talking about actually performing the experiment over and over and over again and keeping track of the number of times our event is that we want occurs, and we're going to divide by the total number of times the experiment is performed. That's really the relative frequency of E. So it's familiar. It should be familiar to you. The law of large numbers, LLN, states that if we keep performing an experiment over and over and over, so in other words, we're collecting a larger and larger sample, we find that the empirical probability or relative frequency of an event E approaches the classical probability, so what we think of as the true probability of E. All right, so if I keep performing the experiment over and over, keeping track of the relative frequency of E, I should find that over time, as I keep doing it, it will approach what we think of as the true probability, the classical probability that we computed before. So for example, we toss a fair die. Sample space is the set 1 through 6, and E is get number greater than 2, right? So E was 3, 4, 5, 6, and last time, of course, the probability of E then is 4 over 6, which is 2/3, which is let me write that as a 0.66666, etc. The 6 repeats. Okay, now suppose we couldn't think of any of this. We didn't have any understanding of sample spaces or anything like that, and we couldn't do this computation, which might seem kind of silly, but suppose we couldn't. Then instead, let's toss the die 100 times. All right, and maybe 3, 4, 5, or 6 comes up, I don't know, 62 times. So the probability of E here is 62 out of 100, right? The number of times it occurred divided by the total number of tosses, the total number of times we performed the experiment. So that's 0.62. All right, it's a little off of 0.6666, right? Well, maybe toss 1,000 times, and maybe we'll find that, let me just go ahead and say, yeah, 3, 4, 5, or 6 happens. Oh, what if we just say 659 times? Okay, now what's the probability of E? It's 659, the number of times it happened, divided by 1,000, and we get 0.659. Isn't that a little closer to that than the 0.62, right? Et cetera, et cetera. Toss 1,000,000 times. 1, 2, 3, 4, 5. Maybe get empirical probability. I want to stress it's the empirical probability to be P of E equals, it might be like, point, or, yeah, well, let's just say it like this. Maybe 6,397 over 1,000,000, right? Which is 0.666397. Okay, so it gets closer and closer, right? If we keep going, the empirical probability will zero in on 0.66666, etc. Okay? That should make intuitive sense to you. That's a good example of the law of large numbers. What about the dartboard example? Okay, well, dartboard example. So, dartboard. So if you remember, the sample space was this, 2 foot by 2 foot, and the event E was 1 foot by 1 foot, right? Okay, I can't figure out that the answer is going to be probability 1/4. It's supposed to be 1 foot by 1 foot. Well, if I can't, I stand back and I throw the dart over and over and over. And remember, we're assuming that we're equally likely to hit anywhere on the board. And what we find is 100 throws. It lands in upper left-hand quadrant, maybe 22 times. Okay, so P of E here is 22 over 100, which I'll write as 0.22. We already know up here that P of E is 0.25, right? The classical probability, the actual probability is 1/4 or 0.25. Oh, so toss 1,000 times. Maybe the probability of E is, it could land maybe 253 out of 1,000, right? So that's 0.253. Okay, etc. It will zero in on 0.25 if we keep going and going and going, tossing it millions and millions of times. All right, that's pretty much all that there is to the idea of the empirical probability. I make a little note at the bottom that says the empirical probability is particularly useful if it's actually hard to calculate the classical probability. Think of tossing a coin. What's the probability of it's coming up heads? The classical probability approach would say, well, there are 2 outcomes. Only one gives you heads, so the answer is 1/2. That assumes the outcomes are equally likely. If the coin is weighted funny, so that one side is more likely to come up than the other, then I can't simply say, well, it's 1 divided by 2, because that only works if the outcomes are equally likely. Everything we've done here has made that assumption. So what if I have a case where an unfair coin, I'm tossing an unfair coin, what's the probability of heads? Maybe we toss the unfair coin 100 times, get heads, 73 times. toss 1,000 times, get heads, you know, maybe like 754 times, etc. Maybe, here, let me write this like this. Maybe the probability of heads, here's how we would write this, really. We would say it heads towards or zeroes in on the actual true probability, which is maybe it's 3/4, 0.75. And how do I indicate that? I would say up here that I'm thinking of the number of tosses. I could have used the notation I'm using right now on all these examples, but I'm just giving it to you right here. The number of tosses maybe approaches infinity. And all that means is if I keep tossing and tossing and tossing and tossing, getting a larger and larger sample, right, I'll never get to infinity, but I just keep going and going and going, what I might find is that the relative frequency of heads comes out to be zeroes in on 0.75, right? So it's definitely an unfair coin. I had no way of calculating it using these classical methods, because if I just count the outcomes, I get 1/2, right? And that's the incorrect answer. But with empirical probability, I can actually get a good estimate of the true probability if I don't have equally likely outcomes.